Hi everyone, welcome back. So we just finished looking at how we can calculate the force due to gravity between two objects. That's using Newton's development of that equation. What we're going to look at today is basically the difference between weight, apparent weight, weightlessness, and apparent weightlessness. Okay, now it's not actually explicitly stated here in the key knowledge, but it says apply the concepts of force due to gravity and normal reaction force. Okay, this part here, that is apparent weight. That is what the scales read when you stand on them. Okay, it's the normal force. It's the force with which the ground is pushing back up on you to cause you to do whatever to your motion, stand still or accelerate in some way. Okay. And we're going to look at how this applies to people in orbit, like in a space shuttle or something. All right. So, what is weight and weightlessness? What is all this stuff? So you probably already know that weight is defined as the gravitational force exerted on an object. It's just a synonym with gravitational force, pretty much. Okay. Don't confuse weight with mass. Mass is an intrinsic property of an object. Okay, it's the amount of stuff that is in the object, whereas weight is weight depends on where you are in the universe. Okay, so your weight, if you are a 1 kilogram object on the surface of the Earth, your weight would be 9.8 newtons. However, if you were away from any planets at all, anywhere, then your weight would be very, very close to zero. However, your mass would still be 1 kilogram. Okay? All right, so that's the difference between weight and mass. Now, the normal reaction force, or the normal force, is defined for our purposes as the contact force between an object and the surface on which it rests. Okay? In other words, it is the force with which the ground pushes up on you, or the surface pushes up on you. We are going to replace the normal force phrase with apparent weight. Okay, so it is the weight that you apparently feel that you are. So compare this to when you're in an elevator. When you start going up in an elevator, the elevator has to accelerate a little bit to reach a certain speed before it comes to a constant sort of speed. During that acceleration process, the ground pushes up on you with more force than it normally would. And so what you feel is heavier. Okay? You feel as if you are being pulled more strongly towards the ground, when in actual fact, it's the ground that's just speeding up where you're already standing. It's pushing up on you, making you go faster. Okay. Now here's a question. Can an object truly be weightless? Is there anything such as zero weight, zero gravitational force? Well, that's what we're going to look at here. The short answer is no. Okay, so like we just said, the apparent weight is what a scale would read if you stood on it. Okay, it's the force with which the ground is pushing up on you. And here's the guy in the elevator. So if the elevator is accelerating upwards, for that brief moment, this person would feel heavier. Okay, and we've got to look at this in terms of the forces that are acting on the person. Okay, so if this person who is sort of stuck to the elevator floor, if the elevator is accelerating, then the person must be accelerating as well. All right? And if the person's accelerating, they must be experiencing a net force. In which direction is the net force? Well, if they're accelerating upwards, then the net force is upwards, as indicated by this arrow. Now, if you think about the forces that are acting on the person in the elevator, well, you've got the weight force, or the gravitational force, pulling them down, but you've also got the normal force between the person and the ground, pointing upwards. Now, if those are the only two vertical forces that are acting on this person, and the net force is pointing upwards, then the way that you could write a net force equation for yourself is the net force is equal to all the positive forces, we're assuming up is positive, so all the positive forces minus all the negative forces. So now we're going back to area of study 3, we'll deal with forces. All right. And this is not 0. This is equal to ma because the person is accelerating. So now if you were to calculate the normal force, or your apparent weight, you'll see that it's equal to the force of gravity plus this other extra stuff. Okay, so you would feel heavier because you're feeling your own normal weight, which is Fg, plus some extra force that's needed to make you accelerate. Okay, so that's how we have to analyze these like apparent weight situations. All right, so let's do a question. Okay, calculate the apparent weight of a 90 kilogram person in an elevator which is accelerating upwards at 1.2 meters per second squared. So if you draw, a force diagram for yourself, so here's a person in an elevator, their net force is going to be upwards. How do we know this? Because they're accelerating upwards. Okay, so F net is equal to ma. All right, so what are the forces acting on the person? Well, you've got gravity force, or the weight, which we'll just call Fg, and you've also got some normal force because of the contact between the person and the ground. Now, we have to write a net force equation for ourselves, and we're going to pretend that up is the positive direction because that's what we do when we know which direction the net force is. You make the direction of the net force to be the positive direction. So, if the net force is positive, then we have to first add all the positive forces together, which in this case is just the normal force. Then subtract all the negative forces, which in this case is just the weight force or the gravitational force. And we know that the person is accelerating, so we can write the net force as being equal to ma. Okay, now our job is to calculate the apparent weight, or the normal force. So rearranging this, we get the normal force is equal to ma plus Fg, which we can write as ma plus mg. We're assuming here G, or the gravitational field strength, is 9.8 because you're close to the surface of the Earth. 90 kilogram person times their acceleration, 1.2, plus 90 kilogram person times G, 9.8. And that's basically 90 times 11, which is 990 newtons. There you go. So that's their apparent weight. Now, if you wanted to sort of calculate their apparent mass, so like when you stand on a set of scales, it doesn't tell you, oh, you have a weight of, such and such newtons. They convert your weight into a mass in kilograms. So how do we do that here? Well, normally when you're just standing still on the ground, your weight is calculated using just acceleration due to gravity. So you have F equals mg. And so if you wanted to work out your mass as you're just standing stationary on a set of scales, this would turn into mass equals F divided by g. And that's what we can do here. This is a force. We're going to write down what the mass would be if you were standing on some scales which are based off of using 9.8. So you could do 990 divided by 9.8. I actually haven't done this on my calculator because it's not part of the question. It's 990 divided by 9.8. And you end up getting 101 point numbers. Okay, so basically 101, what am I doing? Basically 101 kilos, when normally the person weighs 90 kilos. Okay, so the person feels heavier because that's exactly what's going on. They feel as if they are 101 kilos rather than 90 kilos because the ground is pushing up on them more than it normally does. Okay, so 11b, very similar question, except now the elevator is accelerating downwards. So the ones who are paying attention probably would be able to figure out what their apparent weight would be without doing any calculations. Let's do some calculations though. So you've got the net force pointing downwards because this person is accelerating downwards at 9.8. And that's equal to ma. Okay, what are the forces acting on the person? Well, you've definitely got gravity. Okay, and let's say there is a normal force. Let's just say there is, pointing upwards. Okay, but we know that gravity would have to be stronger than the normal force because the net force is pointing downwards. Right, if you were to write a net force equation for yourself, you'd get F net equals all the positive forces, which in this case is Fg, minus all the negative forces, which in this case is Fn. And our job here is to calculate Fn, calculate the apparent weight. So if we rearrange this, we get Fn equals Fg minus Fnet. What's Fg? Just mass times g. What's Fnet? Well, that's mass times acceleration. Okay, let's pop some numbers in. 90 times g, which is 9.8, minus 90 times acceleration, which is also 9.8. And what do you get? 0. Okay, so the apparent weight is 0 newtons. The scale would read 0. Now think about why that would be for a second. Okay, if the elevator is accelerating downwards at 9.8 meters per second, that should be squared. But the acceleration due to gravity is already 9.8 meters per second squared. Then that means whether or not the elevator is actually there or not, the person is still going to accelerate downwards at 9.8 meters per second squared. Okay, so both the elevator and the person are accelerating at the same rate. So the person doesn't have to be in contact with the elevator to actually accelerate in any way. It's just going to accelerate anyway due to gravity. So if this elevator could sort of fall downwards for an infinitely long period of time, what this person would be experiencing inside this elevator is apparent weightlessness. Okay, they don't have to be in contact with the ground in order to accelerate at 9.8 meters per second squared, because they do that anyway due to gravity. All right, and that's basically the principle behind why astronauts in space shuttles and things like that appear to be floating around. Okay, it's not because there's no gravity. Okay, they are in orbit around Earth, or they're in orbit around the moon or something like that. So there is gravity acting on them, keeping them in orbit. It's just that both the space shuttle and the astronaut are falling towards the Earth at the same rate. Okay, so the net effect is you don't actually have to be in contact with anything to have this thing happen to you, because you would do that naturally anyway. And we say that these objects are in free fall. They are falling without any restrictions or without any other forces sort of making them move in any other way. The only force that's acting on them is gravity. And so they're just falling. Okay, but they're both falling at the same rate. So they don't have to be in contact with each other to sort of make each other move around. They're just going to fall anyway. All right, so this is apparent weightlessness. When your apparent weight is 0, you have achieved apparent weightlessness, and it would feel like you were just floating around. And that brings us to this slide, okay? So apparent weightlessness occurs when there is 0 normal force. And we just said objects in free fall experience apparent weightlessness because there's no other forces acting on it except gravity. Okay, you're not standing on a surface as you fall because the surface is also falling with you. Okay. So things going around a planet, things orbiting planets, satellites, people, they're all in free fall. So they're all going to experience apparent weightlessness, unless, of course, the space shuttle or something begins accelerating in an opposite direction using its thrusters or something like that. And then you'd start playing around with the forces, okay? So question 12, 0G aeroplane experience allows you to feel weightless as you reach the peak of the aeroplane's trajectory. Is this true weightlessness? And how can you compare true weightlessness with apparent weightlessness? Okay, I'm going to leave that for you to answer for yourself. Basically, the short answer is you can't have true weightlessness if there are objects in the universe, because the gravitational field extends out into all regions of space. You have to technically be infinitely far away for there to be 0 gravitational field. So you're always going to have some kind of gravitational force acting on you, unless of course you are in a very specific location between 2 objects where the gravitational field cancels out. Okay, so and that's very rare sort of in everyday situations. Okay, so apparent weightlessness is the fact that you don't feel any normal force, so you feel as if you are not standing on anything because everything's in free fall. True weightlessness, very hard to achieve. You have to be at a very specific location, or you have to be infinitely far away from anyone else. Okay, so basically I just explained this summary question, so you should now be able to explain that as well. I'll leave that for you to do. Otherwise, that's the end of the video. Next time we'll start talking about how objects experience changes in energy. Okay, see you then.